Hi, in this video, we discuss a little bit more about time complexity. As we discussed in the previous video, for understanding what is the running time of this code, we should count the number of elementary operations. So here, let us count what is the number of elementary operations for these three lines. First, we can say maybe it is 1000 because we have 1000 steps of for. But in fact, in each step, we have assign, we have plus, we have looking to element of array. Maybe it is 3000. But also in each step of for, you have I++. You also check, is it correct that I less than 1000? So maybe it is totally, there are 5000 elementary operations. But also before for cycle, you have assigning I assign 0, and also for S, you put 0. Maybe there are 5002 elementary operations. Okay, but if we have such a code, can we also count the number of elementary operations? For sinus, you should understand what is inside it. And in fact, it is typically implemented using the complex formula that use multiplications and sum, and it takes about 20, 30 arithmetical operations, so that totally it can be 20,000 or 30,000 or something like this. And for general code, it is hard to estimate such number, count exactly such number of elementary operations, and people don't do it, and we use asymptotically running time. What is it? We count number of steps that does our code, and such that each step takes some constant time, not very big, but and constant time. And in that case, we write that if it do n steps, the time complexity or running time is TO from the n. And formally, this notation TO from the n means that T, that is time complexity, is at most some constant time n. But this O from the n can means not only time complexity, it can be estimation for any function, and formally can be given like this. And we will use O notation for memory complexity, maybe some other points, and formally it can be defined for any function f that is, if it is O from G, it means that for enough big n, the size of this value of this function can be bounded from have upper bound constant time is function G. So we can say that this blue code have n steps. Each step is constant. Green code also have n steps, and red code have also n steps. But in fact, size of step for the blue code about 2 times smaller than time of one step for the green code, and definitely red code much slower than these two, because sinus works longer than these arithmetic operations. but for all of them, we say that time complexity is O from the n, and also it is the same asymptotic time complexity for whole code if we do it one by one. And when we say about time complexity, then we can estimate what is approximately the size of this value of this function. So if n is about 10 to the 8, then we say that running time is about 1 second. Yeah, and this table, it is about asymptotic time. And but if you want to know exactly what is it 1 second or 1 or 2 seconds about this, then you should estimate the hidden constant for this O notation. But if it is important for you, is it 1 second or 1 minute or 1 hour, 1 day, then it is enough to estimate the asymptotic time complexity. Let us try to apply this idea to one small problem that is following. We have a number p, and we should check whether p is prime or not. So how can we do it? The first idea is following. We just check all numbers from 2 to the p minus 1, and if p divisible by I, then it is not prime. Yeah, but if it is not divisible by any number from 2 to the p minus 1, then we can say that it is prime. Yeah, we can estimate the number of steps here. Number of steps is p. Then the time complexity is O from the p. So you see that there is no n variable. That's why we just use this O from the p notation. And if p is about 2 to the 6, so 1 million, then it is about 1 million operations, and it takes about 10 milliseconds, because for 1 second, it should be 2 to the 8 operations. If time limit is 1 second, it is okay. But if we have 10 to the 14, then it is about 10, 11 days. And it is too much for us. Let's look how to improve our code. So firstly, for example, we can check on the numbers up to p over 2, because there is no divisors bigger than p over 2 for any number. So, but anyway, there are p over 2 steps here. It is 2 times faster, but anyway, complexity is O from p, because over 2 is constant, and it's also hidden in O notation. So there are still 10 to the 14 operations, and it is about 10 days, or for, okay, maybe 5 days, but still days. It's not what we need. So that's why we try to improve our algorithm more. We can see that if we check some numbers, and p is not divisible by some numbers from 2 to d, p is not divisible to all of these numbers, then it cannot be divisible by any numbers that is pair for this number. I mean, cannot be divisible by p over 2 and so on, p over d. Why it's so? Because if, for example, p divisible by number b, and b is bigger than p over d, then it should be pair such that b times b pair number a, such that b times a is p, And in that case, A is P over B, yeah, because A times P is P, and it should be less than D because of this condition. That's why we have a contradiction, because we know that P is not divisible by any number from 1 to D. So it means that if we check some numbers until D, then we shouldn't check any numbers bigger than P over D. So we shouldn't, our upper bound also becomes smaller and smaller. If we choose D equals to square root of P, then these two borders D and P over D are equal, and it is enough to check until this border. So we have such a code, and there are square root of P steps, and we know that there are if P is 10 to the 14, then a square root of P is 10 to the 7 operations, and it is just 100 milliseconds. We can improve a little bit our code if we find some number I such that P is divisible by this number I, then we can break our for loop, and code becomes faster. But in fact, the time complexity will be the same, because if P is prime, then we never break it. But if it's not prime, then we stop there. It means that for many numbers, we improve our time complexity, but worst time complexity is still the same. But if we improve our time complex, our program for some users, it is better than don't improve for any user. I mean, if 50% or 80% of users obtain better applications, it is also very good. That's why such improvement is also useful. But our code can be incorrect if P is 4, because if P is 4, it is square root is 2, but it can be not square root sqrt from P can be not exactly the 2, but it can be 1.9999, and in that case, this 4 doesn't do any step, and we don't find these two numbers that is such that 4 divisible by 2, and it says that 4 is prime number. What can we do in that case? We can just put here +1, but this code is incorrect if P is 2. So it checks square root of 2 is 1.4. And for here, check the number I equals 2 and says that 2 is not prime. So what can we do? We can just add this if statement, for example, or put here +0.5. I mean, here in this problem, you should look to some corner cases where your code can have bugs, and such a bugs with corner cases is very hard to find, and it is important to check them to understand where you could work or not. Thank you for listening to this video.